Welcome back. In this video, we are going to solve problem 7-16 that is taken from chapter number 7, Internal Forces, and book name is Static and Dynamics by R.C. Hibbeler. So statement is determine the internal normal force, shear force and moment at point C of the beam. So you can see this is a simply supported beam AB having pin support at point A and a roller support at point B. We have a load which is shown over here. This is a mixture of uniformly distributed load and triangular load. So let's start with the solution. The first step is that I have to draw the free body diagram of this beam. So this is your point A and this is your point B. So at A, when you remove this pin support, so you will be having a normal reaction force vertical, which is represented as AY, as well as you will having a horizontal reaction force AX. Similarly, for roller support, if you remove it, offer only normal vertical reaction force, which is represented as BY. The total length of the beam is 6 meter. Okay, this is 6 meter. Now you can see here we are going to split this load into two type of load. One is distributed load having a magnitude of 200 Newton per meter. So for that I will draw a rectangular like this. It will be like this. You can see this is uniformly distributed load, and this load will have a magnitude of 200 Newton per meter. I will choose another color. For that, if I draw a line from here, so this will be 200, and here we will have another second load, which is triangular load, that is shown in the form of green color. I will draw it like this. Here the magnitude is 0 and here the magnitude will be equal to, total is 400, so 400, and this is 200. So this remaining will be also 200 Newton per meter. So I will draw a rectangle like this, and this will be the triangular load. Here the unit will be magnitude will be 200 Newton per meter. Okay, now we will solve this for finding the unknown reaction forces, which are AX, AY and BY. So for that I will apply the equation of equilibrium. The first equation of equilibrium is that sum of all forces along x direction must be equal to 0 and force toward right is taken as positive. So from this free body diagram you can see only reaction, horizontal reaction force is AX. There is no other force. So it means that AX is equal to 0. Now we'll find this AY by using the second equation of equilibrium, that is sum of all forces along, sum of all moment about point B is equal to 0, because we are going to remove this BY, so that we have equations that contain only AY. So for that, sum of all moment about point B is equal to 0. Now it's time to convert this distributed load 200 load into a point load. So when you convert this 200 load into point load, it will act at the middle of this beam. So this distance will be 3 meter, because distributed load also act at the mid of beam from either side. So this is 3 meter and this is also 3 meter. What will be the magnitude of this load? So it will be equal to 200, which is the magnitude, multiplied by the length over which it act, and the length is 6 meter. So that will be equal to 1200 Newton load. Okay, now the second load is this triangular load, and this triangular load when converted into a point load, so it will be like this, clear, and the magnitude will be equal to 1 over 2 its magnitude, which is 200, multiplied by the length over which it acts 6, and that will be equal to 600 Newton, and that will act at a distance of L by 3 from this denser side. So total length is 6 meter. So 6 by 3 is equal to 2 meter. 2 meter. And this remaining will be the fourth this remaining will be 4 meter. Now we'll apply this equation. So you can see the first force which is producing movement about point B is this force, which is 600 Newton, and the perpendicular distance is 2 meter, and it is producing counterclockwise movement, so it will be taken as positive. So I can write 600 multiplied by 2. The second force that is producing movement is this force, which is 1200 Newton, and perpendicular distance is 3 meter, and it is also producing counterclockwise movement, so it will be also positive. So I can write plus 1200 multiplied by 3. The last force that is producing movement about point B is this force multiplied by perpendicular distance is 6 meter, and this is producing clockwise movement, so it will be taken as negative. So I can write minus AY into 6 is equal to 0. So from here what we will get, this is 1200 and this is 3600, minus 6AY is equal to 0. So 6AY is equal to 4800, and from here you will get AY will be equal to 4800 divided by 6, and that will give you AY will be equal to 800 Newton load. So this is AY. Now you can find this BY by using third equation of equilibrium, that is sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So the vertical forces are AY plus AY minus 1200 minus 600 plus BY. Their sum must be equal to 0. So I can write AY minus 1200 minus 600 plus this plus BY is equal to 0. So AY is 800 minus this is 1800 plus BY is equal to 0. So from here this will be minus 1000 plus BY is equal to 0, and we will get BY will be equal to 1000 Newton. Now we have these reaction forces. So what we are going to do, we have been asked to find the normal force, shear force and moment at point C of the beam. So what we are going to do is that we will cut the beam at point C and we will draw the free body diagram. And for that we will take this left hand side. You can also take the right hand side as well, but we will take the left hand side of this beam, which is section AC. So for section AC, the free body diagram will be like this. Let this is section A, this is point A, this is point C. At point A, you know you have a vertical reaction force AY, which is 800 Newton, and AX, but AX is 0, so no need to mention it. So when you cut it at point C, so you will be having a normal reaction force NC, you will be having a vertical shear which is VC, and you will be having a moment MC as well. And from here you can see this is section is taken till the mid of this beam. So the load will be like this. So this will be 200 Newton per meter load. This is a uniformly distributed load, that is 200 Newton per meter, and for triangular load it will be like this. So this will be triangular load starting from 0 and till mid. You can see this is 200, here it is 0, and here it will be 100 because it is at the mid, and at the end this is 200 meter. So here we can write 100 Newton per meter, and the total length of this beam is 3 meter where it is sectioned. Okay, so let's find this NC, MC and VC by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0 and force toward right is taken as positive. So from this free body diagram you can see only horizontal reaction force is NC, there is no other force. So I can write NC is equal to 0. Now the second thing is that we will find this VC by using the another equation of equilibrium, that is sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So first we will convert this distributed load into a point load. So it will be act in the middle and its magnitude will be equal to 200 multiplied by 3, that is equal to 600 Newton. And this uniformly increasing load, when converted into a point load, it will be equal to 1 by 2 into 100 multiplied by 3, which is equal to 300 divided by 2, and that will be equal to 150 Newton. And that will act at a distance of L by 3 from this denser side, means this side. So L is 3, 3 divided by 3 is 1 meter. And this distributed load will act at the middle, so it will be at a distance of 1.5 meter from either side. Now we can easily find this VC by using this condition of equilibrium. So let's do that. 800 Newton load at point A, which is acting upward. So it will be 800 minus this 600 Newton minus this 150 Newton load minus this VC is equal to 0. So we can say that VC will be equal to 800 minus 750, and this VC will be equal to 50 Newton load. The last thing that we will find is this MC. So for that we will apply condition of equilibrium, that sum of all moment about point C is equal to 0 and taking the counterclockwise moment as positive. So first thing that is producing moment is 800 into perpendicular distance is this 3 meter, and this producing clockwise, so it will be negative. So I can write minus 800 multiplied by 3. The second force that is producing moment is this 600, and perpendicular distance from point C is 1.5 meter, and this is producing counterclockwise moment, so it will be positive. So for that 600 into 1.5. The third force that is producing moment about point C is this one, which is 150, and perpendicular distance is 1 meter, and it is also producing counterclockwise moment, so it will be positive. So I can write plus 150 multiplied by 1, and the last moment, that is reaction moment taken as counterclockwise, so it will be also positive. Their sum must be equal to 0. So minus 2400 plus 1600, 600 multiplied by 1.5 is 900 plus 150 plus MC is equal to 0. So minus 2400 plus 900 plus 150 is equal to minus 1350 plus MC is equal to 0. So MC will be equal to 1350. Unit will be Newton into meter, and when this is converted into kilonewton, so it will be 1.35 kilonewton into meter. And which are the answer of our this question. So in this way we have find out the normal internal force, shear force, and moment at point C of the beam. So this was all about this problem 7-16. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.